Okay, so in this lecture we will be looking at triple integrals. Just as you've looked at single integrals and double integrals double integrals in this course and single integrals in previous courses, we'll look at triple integrals now. Now triple integrals are, of course, when you do a triple integral, you do it over a three-dimensional region. Triple integrals are performed over a three-dimensional region. In other words, the triple integral performed over a volume. In other words, the triple integral is performed over a volume. So we'll start with the simplest possible case. Right? A rectangular region in three dimensions. Rectangular region Cartesian coordinates in three dimensions. Right? So, and by rectangular region I mean a box shape. So in three dimensions, instead of D, we'll call our region E. Right? X comma Y comma Z. X goes from A to B. Y goes from C to D, and Z goes from E to F. Right? So okay, let's do R2. Let's be consistent. Let's use R to S. We want to agree with the bulk. Right? So Z should go from R to S, and the box has this shape. Right? This is our little box. And we can break this, let's call this box B, right? And this is the box over which we're going to integrate. This box. This is our box of we can call this our box of region. This is the region of integration, which is a box. Right? Now, as before, we can break this big box into smaller sub-boxes. Right? We can break this big box into smaller sub-boxes. How do we do that? The x interval, AXB, break this interval, the x interval, into L subintervals. Then you break this interval, the CD interval, into M subintervals, and the last interval, break R comma S into N subintervals. Right? Now, if that is the case, then the length of an x subinterval, delta x, is given by, this is the length of an x subinterval, this is given by V minus A over L. and delta y is given by d minus c over L, and delta z, sorry, d minus c over m, not L, but m. And delta z is of course given by s minus r over n. Right, so the volume, so these subintervals, right, the fact that we've broken down each of x, y, and z into so many subintervals, this tells us that our big box, right, the big box that we had, the big box region of integration, is now broken down into LMN sub boxes, right? So for each and each sub box, I mean each smaller box has each smaller box, each sub box. A sub box is like a subinterval. Sub box has volume. Each sub box has volume. Of course, delta x, delta y, delta z. Just like this, right? So our big box of integration is B, and that big box has been broken down into LMN sub boxes, and the volume of each sub box is delta x times delta y times delta z. Now, since there are LMN sub boxes, consider a representative sub box. Right? Consider the sub box. Consider the Vijk sub box, where I is of course goes from 1 to 1 to L, J goes from 1 to M, and K goes from 1 to N. Now the Vijk sub box is made of the interval. So this Vijk sub box has these dimensions, right? Has these intervals as its dimensions. So on the x-axis, in the x direction, Vijk, this is xi cross yj minus 1 comma yi cross zk minus 1 yj zk. So this is the Vijk sub box. Right. Now let's draw this sub box. Let's draw this Vijk sub box, and let's just to illustrate the V, and let's use a representative point inside that sub box, right? So this is the right? This is the Bijk sub box, right? And inside the Bijk sub box we have the points xijk star, yijk star, and zijk star. Now where xijk star is in this interval x minus 1 xi, yi jk star is in this interval yi minus 1 yi, and zijk star is in this interval, right? Zi minus 1 zi. And of course this sub box has a volume of delta x times delta y times delta z. Let's form the triple Riemann sum, right, over all the sub boxes. Let's form the following triple Riemann sum. When you did double integrals, remember you had a double Riemann sum. Now we're going to do a triple Riemann sum. So I goes from 1 to L, J goes from 1 to M, and K goes from 1 to N. F of, now we evaluate F at representative points y star ijk, comma z star ijk times delta x, delta y, delta z, right? And of course this sample point x star ijk, y star ijk, and z star ijk is in the box Bijk. Now delta x, delta y, delta z can be written as delta v. I mean, of course, we're written as delta v. And by delta v, I mean the volume of the subbox, right? The volume of the Bijk subbox, delta v. And now let's define the triple integral over the entire subbox. Let's call it B, the subbox B. Define the triple integral. We're doing the integration over B, f of x, y, z, and of course we're doing the integration over a volume, and this is going to be equal to limit L goes to, in fact, limit L, M, and N, all three go to infinity. L, M, N, they all go to infinity. I is equal to 1 to L, J is equal to 1 to M, K is equal to 1 to N. F evaluated x star ijk, y star ijk, z star ijk, delta v. Right, so this is the definition of the triple integral over the box. This is how the triple integral is defined over the box. Now when when L, M, and N, they go to infinity, right? When L, M, and N, they go to infinity, then these intervals xi minus 1 xi, yi minus 1 yi, zi minus 1 zi, these intervals, they're essentially 0. So it does not really matter which point I pick inside the interval. I could pick xi minus 1, I could pick xi, any point in the interval. So I can write this as, right, so I could choose any sample point in the sub box. It doesn't necessarily have to be x star I, j, k. So I could write this as v f of x, y, z dv equals limit as L, M, N go to infinity, I equals 1 to L, j equals 1 to M, k equals 1 to N, f of xi, yj, zk, delta v. Alright? Okay, so this is the definition of a triple integral. Definition. In fact, both of these are the definition of a triple integral. Right. Now, remember, we know of this theorem called the Fubini's theorem, which actually helps us evaluate integrals in a practical way. So if just as with double integrals, we can use Fubini's theorem with triple integrals. Fubini's theorem with triple integrals. Right, so if you want to evaluate the integral over box x, y, z dv, this is actually equal to remember the x and remember our limits were a to b for x, c to d for y, and r to s for z. So I could write this as r to s for z, c to d for y, and a to v for x. Z dx dx dy dz, right? And of course you are free to evaluate this in any order you feel like. This can also be written in as a to b, r to s, c to d, f of x, y, z, dy, and of course r to s is in dz, dx. Right? You could do that. In fact, there are 3 factorial, 6 possible orders of integration. Right? 6 possible orders of integration. Okay, so let's try to evaluate an integral over a triple integral over a rectangular region. Let's see what we can get. So let's try to evaluate this integral. So we're given a region B. B equals, this is a rectangular region. X goes from 0 to 1. Y goes from -1 to 2. And Z goes from 0 to 3. And we want to integrate, and we want to find and of course f of x, y, z. We're given a function of x and y and z, which is equal to xyz squared. xyz square. We want to find xyz dv. We want to find this integral. So it's this is something that can be evaluated using Fubini's theorem. Let's try to evaluate this using Fubini's theorem. So this can be written as dv can be written as dx dy dz. So z of course goes from 0 to 3, y goes from -1 to 2, and x goes from 0 to 1. So x, y, z square dx dy dz. So let's do x integration first, this integration first. So this is going 0 to 1 xyz square dx is of course going to give me half x square y z square, x equals 1, x equals 0. So this is equal to half y z square. So this is equal to 0 to 3 minus 1 to 2 half y z square dy dz. Now let's do the next integration, which is minus 1 to 2 half y z square dy. This is actually equal to 1/4 y square z square from y is equal to 2, from y is equal to -1 to y is equal to 2. Right? And this gives me 1/4 times 4, which is 1, so which is z square minus 1/4 z square, which is equal to 3/4 z square. So we are now going to evaluate 0 to 3 3/4 z square dz. Okay, so so this is actually equal to 1/4 z cube, right, from z equals 3, from z is equal to 0 to z is equal to 3. So this becomes 27 by 4 minus 0, which is 27 by 4. Okay, so integration over rectangular regions is pretty easy. I mean, integration over boxes is easy. How about integration over more general regions? So remember, we had type 1 regions and type 2 regions and type 1 and type 2 regions with double integrals. Double integrals. We had type 1 and type 2 regions. Now with triple integrals, So now we're dealing with integration over general regions. Integration triple integration over general regions. So we had type 1 and type 2 regions, right? And with triple integrals, you're going to have type 1, type 2 and type 3 regions, right? So a type 1 region is a region which is a way of describing a region where you have z fall between two functions of x, right? You have z falls between two functions of x, sorry, x and y. Z type 1 region, type 1 region I'm going to call it E, x comma y comma z. So x comma y is in D, right? So D is the projection of E onto the xy plane, and z falls between two functions of x and y. So z is between u1xy and u2xy, right? So z is between two functions of x and y, and of course D is the projection of E on the xy plane. So let's have a look. So you have this general region E, and D is the projection of E on the xy plane. Now D may be a type 1 region. Now where does D get involved? So if this is the case, right? If this is the case with our if we're dealing with a type 1 region in 3 dimensions, right? So our integration, let's call it E, f of x, y, and z dv is going to be equal to, so you first do the first thing you need to do is you do the z integration, right? So z is between two functions of x and y, u2 xy, f x y z dz. You do the z integration first, and then you integrate over D, right? So D may be, again, D itself may be a type 1 region or a type 2 region. D may be a type 1 or a type 2 region, meaning D. Now when we say that D may be a type 1 or a type 2 region, we mean that D may be a type 1 or type 2 region in 2 dimensions. In 2 dimensions. Right? Now recall that when we're dealing with 2 dimensions, a type 1 region is one that is between 2 functions of x, and a type 2 region is one. A type 1 region is where y is placed between 2 functions of x, and a type 2 region is where x is placed between 2 functions of y in 2 dimensions. Now, if D is a type 1 region, if D is a type 1 region, if that is indeed the case, then E can be written as follows. The set of all coordinates x, y, z such that x is between 2 constant values, y is between 2 functions of x, g1x and g2x, and z is of course as before between u1xy and u2xy. Right, so E can be written in this form if of course E is a type if D is a type 1 region. And now if D is a type 2 region, okay, before that we can let's write down the integral, right, over E fxyz dv can be written as this integration with respect to x you do last, g1x to g2x, the second this is the second last integration or the second integration, and this is the first integration with respect to x and y, to x and y, right? Now of course you have fxyz dz dy dx. Right, so this is the this is type 1 integration. Now if D is a type 2 region, let's go back to D being a type 2 region. If D is a type 2 region, then we may write E as x, y, z. Now y is going to be between 2 values of x, right? So x is going to be between 2 functions of y. Y is going to be between 2 constant values, and x is of course going to be between h1y and h2y, and x and z is of course going to be between 2 functions of x and y, u2 x y. Then we may write the integration as, over the region E, fxyz dv equals remember, always do the integration with the constant limits at the end. It's cd h1y h2y, and you have u1xy u2xy f x y z dz dx dy. So this is if D is a type 2 region. So when it comes to E being a type 1 region or a type 2 region or a type 3 region, and D being a type 1 or type 2 region, there are 6 possibilities, right? Because for each type that E has, there are two possible types that D can take. So for example, let's look at 3-dimensional regions that are type 2. Okay, let's before that let's do an example, right, of a region where you have type where the region is of type 1, and try to evaluate the integral, I guess. Okay, so this is example 2 from your textbook. Example 2 from your textbook basically says that you have to evaluate z dv, right? The integration of z dv right, where E is a solid bound in the first octant, bound by the surface z equals 12xy, the plane y is equal to x, and y is equal to 1. Right, so E is the solid in the first octant. E is the solid in the first octant, bound by the surface z equals 12xy, and the planes z equals 0, z is equal to 1. Right, so these two, sorry, not z is x, planes y equals x and x equals 1. Sorry, planes y is equal to x, y equals x, and x equal to 1. Right, so when we're obviously when we're drawing the region, when we're setting up our integration, right, it's always important to start off with a sketch, right? So we start off with a sketch. First of all, the first sketch that we do is we sketch the we have to sketch 2 regions, right? Sketch the volume over which you are integrating, right? And this is the region E. And the second thing you need to do is sketch the projection of that volume onto the xy plane. Now this is of course when you're dealing with type 1 surfaces. So let's have a look at this type 1 surface. So the sketch is actually done for you. For this, of course, you will need some form of graphing software. You will need some form of graphing for part 1 at least. You will need some graphing software, right? For example, GeoGebra, or so you could use GeoGebra. You could use GeoGebra and Python are free. Mathematica is of course paid, right? So now let's have a look at the region. It's already sketched out for us, right? So the plane y equals x, of course, makes it's basically an extension of the line y is equal to x above and below the xy plane. So, and you have the plane y equals 1, and you have the surface that equals 12xy. So this is the region E. So the region E has, since the region E is in the first octant, we may write it this way: E is a set of those points x, y, z such that x now y goes from 0 to x, 0 to x goes from 0 to 1, x goes from 0 to 1, and z goes from 0 to 12xy, right? So this is the region D, right? X goes from 0 to 1, y goes from 0 to x, and z goes from 0 to 12xy. Now this is this part is of course the region D, and this is type 1, right? Alternatively, we could have written D as a type 2 region, right? As in x, y, z, 0 x, y, 0 x, y, 0 y, 1, 0 z, 12 xy, right? So this is where D is a type 2 region, type 2. But in both cases, E is a type 1 region. In both cases, E is considered a type 1 region. Now let's go back to this diagram. Now notice something here. Now if the left diagram, the blue diagram, is the diagram, it shows you E, and the green diagram shows the projection of E on D, on the xy plane. Now here D is considered to be a type 1 region, and once you do that, and once you've figured out the region of integration, the actual integration, since the function is just z, the actual integration is pretty easy. So however, what you need to watch out for is the order of integration. So the z integration first, then the y integration, then the x integration, if D is a type 1 region. Why? Because the z integration is going to give you a function of x and y. Then the x integration and then the y integration is going to give you a function of x, and then the x integration is going to give you a constant. So please maintain this order when we're given the variables, right? So z, dz, dy, dx. So when you integrate with respect to z, you get z squared by 2, and you integrate from 0 to 12xy, and you get a half times, you get 72x squared y squared, right? And then you do the y integration, right? So y cubed by 3, y goes from 0 to x, and you end up with x to the 5, 24x to the 5. Then you do the x integration, you end up with 4. So figure 7 shows the solid E of example 2 is swept out by the iterated triple integral if we integrate first with respect to z, then y, then x. Right? So when you're integrating with respect to z, you're going from the xy plane all the way to 12xy. When you're integrating with respect to y, you're going from 0 to x. And when you're integrating with respect to x, you're going from 0 to 1. Right. Now let's look at type 2 regions. Type 2 and type 3 regions. They're very similar to type 1 region. So type 2 region is where x is between two functions of y and z. Type 2 region in 3 dimensions x, so if x comma y comma z, x comma y is in some domain D, is in some region D, and z x comma z is in some, y comma z is in some domain D, and x is between two functions of y and z. So that's the type 2 region, right? And a type 3 region is where y is between two functions of x and z. Right? Y is between two functions of x and z. That's the type 3 region. Okay, in the type 2 region, D is the projection of E on the YZ plane, not the XY plane, but the YZ plane. Right? And a type 3 region let's look at a type 3 region. E given by x comma y comma z, so x comma z is in D, and y is between two functions of x and z. U2 x and z. Right? So D is the projection of E on the xz plane. Alright, so that's a type 3 region. Okay, so let's look at an example for an integration. Okay, so this is a type 2 region. X is between two functions of x, y and z, and the projection is on the yz plane. And this is a type 3 region where y is between two functions of x and z, and the projection is on the xz plane. Right. So okay, so in the type 2 region, the integration is carried out first. The x integration is carried out first. X integration carried out first in the type 2 region, and in the type 3 region, y integration carried out first. Okay, so let's look at an example of a type 1. Let's look at an example. Okay, let's so in this example, we're integrating x squared plus z squared, where E is the region bounded by the paraboloid y is equal to x squared plus z squared and the plane y is equal to 4. So from on the surface of it, it makes sense to consider this as a type. So since y is between two functions of x and z, this is a type 3. It looks like a type 3 region, right? Let's look at this as a type 3 region. Instead of a type 1 or type 2, let's look at this region as a type 3 region. So, and the projection D is basically the intersection of the plane y is equal to 4. This D is the D3 is the projection of the intersection of the plane y is equal to 4 and the paraboloid surface. On the paraboloid surface, what's the paraboloid surface? Y is equal to x squared plus z squared onto the xy plane. This is not the xy plane, onto the xz plane. xz plane. Now this intersection is of course going to give you the circle x squared plus z squared is equal to 4. We're going to get a circle x squared plus z squared is equal to 4. So that is D3, the region D3, right? Okay, so let's try to do the integration, right? So what we're doing is so E is given by we need to we are only given the z limits, right? We need to figure out the y limits and the x limits. So this is our E. This is example 2. Let me write that in red. Example 2. This is from page. This is from page 1086 and 1087 of the Stewart textbook, right? Page 1086 and 87 of the Stewart textbook. Right. So what is a region of integration? Our region of integration is as follows. Region, our volume of integration, or a region of integration, E x, y, z. So x and z are in some d3, and y is y goes from x squared plus z squared, which is the lower limit for y, and the upper limit is 4. So this is the region of integration. Now given that this is the region of integration, we need to first things first, we need to figure out d3. So d3 is the projection d3 is a projection of E on the xz plane. d3 is the projection of E on the xz plane, and d3 is the circle. So this is the circle x square plus z square equals 4, right, on the xz plane. Now you could think of d3 as a, now we'll do the integration over d3 later, but first let's do the integration over over the y limits, right? So we have to integrate x squared plus z squared dv, square root of x squared plus z squared dv, square root of x squared plus z squared dv. This is equal to the integration of d3, right, times the integration from x squared plus z squared to 4 of the square root of x squared plus z squared dy times dv. So let's do this inner integration first, right? This integration should give me, go from x squared plus z squared to 4, then you have x squared plus z squared to the power of half dy. This is equal to y times x squared plus z squared to the power of half, and of course y goes from 4 to x squared plus z squared, and you should end up with 4 times x squared plus z squared to the power of 3, to the power of half, x squared plus z squared to the power of half, minus x squared plus z squared to the power of 3 by 2. And then you take this out, x squared plus z squared, take this out, and this becomes 4 minus x squared minus z squared. So x squared plus z squared half, you take this out. Right, so now the integration over d3, is this, d3 of what? X square plus z square. 4 minus x square minus z square half dA, right? Now what is the, now we could try expressing this circle as the circle, the disk D3. In fact, this is not a circle. Again, this is a disk. This is the disk. We could try expressing this disk as a type 1 or a type 2 region, but that would give us a lot. That would give us a lot of grief, a lot of unnecessary difficulties. The easiest way to do this integration, easiest way to do this integration is to convert to polar coordinates, right? Is to convert to polar coordinates. So we said r square is equal to x square plus z square, right? Polar coordinates on the xz plane now. Well, and theta, tan theta equals z by okay, it equals z, yeah, z by x, right? Tan theta is z by x, because x is r cos theta, y is r sin theta. X equals r, sorry, r cos theta, z equals r sin theta. So the disk D3 then can be represented, this disk D3 can then be represented in the following fashion. Let's say a disk D3, remember, the disk has radius 2. Radius equals 2, right? Because why is the radius 2? Because the disk is given by x square plus z square is less than or equal to 4, and radius 2, and theta of course goes from 0 to twice pi. So D3 r theta, r goes from 0 to 2, right, and theta goes from 0 to twice pi, right? Now that we know this, we can now the region of integration is a whole lot easier. And of course, this can x square plus z square square root can be written as r, and 4 minus x square minus z square. Remember, this can be written as, this is equal to r, and 4 minus x square minus z square is 4 minus r square, and dA can be written as r dr d theta. Right, so let's do the integration. D 0 to twice pi, r dr goes from, r goes from 0 to 2, and this can be, and of course this can be written as r. You have a 4 minus r square, r dr d theta. You could write this as an iterated integral, 0 to twice pi d theta, 0 to 2 r square, 4r square minus r to the 4 dr. So this is equal to twice pi, 4 over 3 r cubed minus 1 over 5 r to the 5, 2 to 0. I mean, obviously r equals 2 to r equals 0, twice pi, 32 by 3 minus sorry. So to get to the answer, for r cubed minus r to the 4, that's fine. Sorry, 4r square minus r to the 4, 4 by 3 r cubed minus 1/5 r to the 5. So 8 times 4 is 32 by 3 minus 32 by 5. This can be written as twice phi. 64 phi. Right, and okay, so 5 by 15 minus 3 by 15, 2 by 15, 128, 5 by 15. Alright, so this is the integration, right? So the most difficult step in evaluating a triple integral is setting up an expression for the region of integration, right? So remember that this is actually a very important point. The limits of integration in the inner integral contain at most 2 variables. The limits of integration in the middle integral contain at most one variable, and the limits of integration in the outer integral must be constants. Memorize this, keep this in mind. And of course, Fubini's theorem enables us to change the order of integration as we wish, right? But if you're going to change the order of integration, you have to convert. You have to keep this in mind. Make sure that the middle integral does not contain 2 variables, or make sure that the outer integral does not contain 1 variable. Okay, just keep this in mind. So for example, we have this triple integral, this iterated integral, 0 to 1x, 0 to x square y, and 0 to y, where x is the 0 to y, these are the limits for x, dz, dx, dy. Right, now we want to integrate first with respect to z, first with respect to x, then with respect to z, then with respect to y. Okay, let's see what these what the region looks like, what the solid E looks like. Right, this is the solid E. X goes from the plane x is equal to 0. The plane x equals 0 is of course the now if we're talking about x equals 0, then that's the YZ plane, right? X equals 0 is the YZ plane. To x equals 1, and of course by x equals 1 we mean a plane that is parallel to x equals 0, and y goes from 0 to x squared, right? So the surface y is equal to 0 to the surface y is equal to x squared, and z goes from z equals 0 to z equals y, the plane z equals y. So we have so this is our region E, and the region in blue. This is the region E. Sorry. This is our region E. Right. So now if you want now the projection of E onto the xy plane. So this is the region E. The projection of this region E onto the xy plane can either be written as a type 1 region or a type 2 region, right? Meaning it could be that y is between two functions of x and x is between two functions of between two constants, or it could be that x is between two functions of y and y is between two constants, right? So this is D1, the projection on the xy plane, right? So you could write y is equal to x squared is x equals root y. Again, this is type 1. So we have type 1 and type 2 on the type 1 and type 2 on the yz plane, and we have type 1 and type 2 on the xz plane. Right? So this is the xz plane. Type 1 and type 2 on the xz plane. So the projection on the yz plane is of course y equals. So when we're talking about the projection on the yz plane, this x square is excluded, of course. Is it alright? So once we look at the projection, right? So in order to integrate first with respect to x, now we want to integrate. We want to do the integration first with respect to x. So we want to do this integration, right? So we want to do f x, y, z first with respect to x, then with respect to respect to z, then with respect to y. So the inner integral can contain at most can contain at most two variables. The outermost integral cannot contain any variables, right? So if you want to integrate with respect to y last, for example, so y must of course then lie between two constant values of between two constant values. So where among all of these regions, where does y lie between two constant values? So one way of so there are two cases, right? So in this case y lies between 0 and 1. In this case also y lies between 0 and 1. So these two are possibilities, right? These two are possibilities. Now we want to first of course we want to first integrate with respect to x, right? So x should lie I mean if we want to integrate with respect to x first, then of course x is going to be between two functions of y, right? So x is going to be between two functions of y, square root of y to 1, right? So x is going to go from square root of y to 1. The thing is that we want y to lie between two constant values, and z is of course then going to be between 0 and y, right? Z is going to be between 0 and y. 0 and y. And of course you first integrate with y, then with respect to x, then with respect to z. So if you want to do that, z has to lie between two constant values, right? Z has to lie between two constant values. So one way you could do this is 0 to 1. Y could what's the second variable? Then x and then z. So then x, and there's f of x, y, z, dy, dx, dz. So z has to be between 0 and 1. Well, this works and this works, right? And x fine. Now if z is between 0 and 1, right, what could x be between? The thing is that we don't want x being between two values of z, right? We don't want that, because we don't want x being between two values of y, right? Why would that be a problem? Because if x were between two values of y, well, we've already integrated with respect to y first, right? And if x is between two values of y, well, we'll be bringing back y. We don't want that to happen. So one way of looking at it is, of course, is to have y go between 0 and x squared. Just give me a moment. So y could go between 0 and x squared, and z and x square, not 0 and x square, z and x square, because the lower limit is z and the upper limit is x square, right? So y could go between z and x square, and x could go between 1 and the square root of y, right? X could be or between the square root of z and 1, right? So x is between the square root of z and 1. Square root of z and 1. This region. This is one region that we could select, right? And yeah, and we're done. So we need to select a type 3 region, actually, right? So if we want to integrate with respect to, or if we want to integrate with respect to y first, then we'd need a type 3 region, right? And in order to integrate with respect to x first, actually just keep this in mind. Integrate with respect to y first. Integrate with respect to y first. Actually, let's do z first. You have a type 1 region. If you want to integrate with respect to x first, you have a type 2 region. And if you want to integrate with respect to y first, then you have a type 3 region. Okay. Alright, now, of course, the first application of triple integrals, the one that you obviously need to know, is that the triple integral, if you integrate with respect, if you integrate 1 with respect to dv, I mean, if you integrate 1 over the region of v, I mean, if you, okay, let's write it this way: e1 dv. This is the volume of the region E. Right? If you integrate 1 on the region E. Now let's think of it. This is a type 2. I think of this as a type 1 region, right? So D is the projection right? On the xy plane, as a type 1 region, you have u1 xy, u2 xy, you have dz, dx. Actually, let's not call it dx, let's call it dA. Right. And of course, this is going to give me u2 xy minus u1 xy dA. So remember, this integral gives me the volume under the surface u2 xy above the xy plane, and this integral gives you the volume under the surface u2 xy above the xy plane, right? So this so the integration obviously gives you the volume bound between the two surfaces, right? The volume bound by the two surfaces. Okay. So let's look at an example. Use a triple integral to find the volume of the tetrahedron T bounded by the planes x plus y plus 2z is equal to 2, x equals to y, x equals 0, and y equals 0. Right? So remember, when doing triple integrals, we sketch the region E itself, and we sketch the region D, that is the projection of E onto some plane, either the xy plane or the xz plane or the yz plane. Right, now let's have a look. Let's sketch the the region. In fact, those regions they're actually sketched for us. Right, so the tetrahedron T is of course given by the planes x equals twice y, x plus twice y plus 2 is z is equal to 2, and you have the yz plane, xy plane, which is z is equal to 0, and you have the plane. You have the zy plane, which is x equal to 0, right? So your E or your T, whatever you choose to call the region, has x, y, z. Now the projection of this region. So first of all, you write it this way: x, y, and d, and then z goes from 0 to 2 minus x minus 2y, x minus 2y. Right. So this is the region T. Now this region, the projection of this region on the xy plane is a triangle. You can think of this triangle as either a type 1 region or a type 2 region. The region D can be either thought of as a type 1 region or a type 2 region. Now, of course, the edges of the triangle are y is equal to x by 2 and x plus and y is equal to 1 minus x by 2. Okay, this is a type 1 region. So remember, the inner integral, at this two variables, right? This integral, the second integral has one variable, and this integral has constant limits. Constant, that's one variable in its limits, two variable in its limits, right? Okay, so obviously there are many applications to triple integrals, just as there are to double integrals, such as finding the moment of inertia or integrating the density. I could go over these applications if you pick at least two applications that you would like to do, and you could do these integrals, right? Now the next thing that we're going to do is we're going to look at triple integrals in cylindrical and spherical coordinates. Okay, so cylindrical coordinates are defined by they're related to Cartesian coordinates by these equations, right? X is equal to r cosine theta, y equals r sine theta, and z is equal to, the z in cylindrical coordinates is the same as the z in Cartesian coordinates, right? And to go from Cartesian to cylindrical, use r square equals x square plus y square, tan theta equals y by x, and z equals z. Now the question is, what is the measure of integration on cylindrical coordinates? As in, what is our dv equal to, right? So in Cartesian coordinates, our dv is dx, dy, dz. So that's in Cartesian coordinates, right? What about cylindrical coordinates? In cylindrical coordinates, remember, cylindrical coordinates in two dimensions are basically, these are, r is distance on the xy plane, distance on the xy plane, right? And theta is the angle on the xy plane. So when you use cylindrical coordinates, you're basically using the polar r that you already know from two-dimensional coordinate geometry. This is for polar coordinate, the same as the polar coordinate r, and this is the polar coordinate theta, and of course this is the coordinate z, Cartesian coordinate z, Cartesian coordinate z. Now remember, the dv equals dx, dy, dz. Now dx, dy, dz. Now dx, dy, remember, in polar coordinates we found out that this could be expressed as r dr d theta, right? In polar coordinates, dx, dy could be expressed as r dr d theta, and dz remains the same in Cartesian and in polar coordinates. So dv can be written as r dr d theta dz. This is of course something that we will derive using a method called a Jacobian determinant, right? But that's a little later, right? We'll have a very short lecture on the Jacobian determinant right after spherical coordinates, right? So if you would like to integrate into triple integrals in cylindrical coordinates, you basically change your x, y, z to r cos theta. So this is the formula, right? You have E f x, y, z dv this can be written as so z is between two functions of r and theta, so let's say you have h1 of r theta and h2 of r theta, right? And of course you have f r cos theta, r sin theta, comma z, and don't forget the r dr. Sorry, first thing you write is z, because this is the inner integral, r dz, and then let's say dr d theta. I mean, depending on how you define your region, right? So r could be between some g1 of theta and some other g2 of theta, and theta could be between alpha and beta, right? So this is the region in cylindrical coordinates. In cylindrical coordinates, you could describe this as r comma theta comma z. Your theta is between alpha and beta, which are constants. R is between g1 of theta and g2 of theta, and z is between h1 of r and theta and h2 of r and theta, right? So this is one way of describing the region, right? So let's do this integration. So there are plenty many examples of cylindrical coordinates, but let's do this one example where we are to evaluate x square dv, where E is the solid that lies under the paraboloid z equals 4 minus x square minus y square and above the xy plane. Right now, the symmetry of E tells us that cylindrical coordinates are the best choice, and you start picking up these symmetries, you know, when you get better at this as you practice, right? So x square. Now, how do we express this region in terms of cylindrical coordinates? Now, the projection of E onto the xy plane is a disk. Projection of E onto the xy plane is the disk. Which disk? X square plus y square is less than or equal to 4, right? Meaning it's bound by the circle. R is equal to 2, right? So R goes from 0 to 2, right? In this projection, right? And then you have theta going from 0 to, so R has to go from 0 to 2, and you have theta going from 0 to twice pi, and you have z. Remember, the upper limit is 4 minus x square minus y square. This can be written as 4 minus r square. So z goes from 0 to 4 minus r square, and the integrand, the expression we are integrating, x square equals r square cosine square theta, and the measure dv is again r dz dr d theta, right? Because why is z here first? Because we're integrating with respect to z first. because remember z has the highest number of variables and its limits, right? And then r and theta are of course constants, so it doesn't really matter whether you integrate with respect to r first or with respect to theta first, right? And then you carry out the integration, and when you carry out this integration you get 16 by 3 pi. So that gives you the volume underneath this parabola, paraboloid, and above the xy plane, right? So this tells you that z varies from 0 to 4 minus r square, where r and theta are constant. R goes from 0 to 2, while theta is constant, and z goes from 0 to twice pi. Okay, another example of another important coordinate system we will look at is spherical coordinates, right? Doing triple integrals in spherical coordinates. Now, in spherical coordinates, any point can be given by a number, by a length rho. Now, rho is the distance from the origin to the point itself, right? Rho is the distance from the origin to the point. Theta is the angle that the projection of this rho of OP makes with the x-axis, right? So you take OP and you have the projection of OP, right, on the x-axis, on the xy plane, and theta is the angle made by the angle between the x-axis and the projection, right? And phi is the angle between the z-axis and OP. Right, and of course the conversion formula is x equals rho sine phi cos theta, rho sine phi cos theta, because rho sine phi is a projection on the xy plane, and then and of course multiplying that by cos theta is going to give you the x coordinate, and rho sine phi sine theta is going to be the y coordinate, and rho cos phi is going to give you the z coordinate. I think this is something that should be apparent from the diagram, right? And of course, when you add x squared plus y squared plus z squared, and you use your trigonometric formulae, you should get x squared plus y squared plus z squared is equal to rho squared. All right. So next thing we do is we're going to do triple integrals in spherical coordinates. Now, in spherical coordinates, the measure is of course going to be different from the measure in Cartesian coordinates. So I'm just going to write down the answer, and we're not going to prove it using the techniques in this section. We're going to prove it using the Jacobian, right? So which we will do in the next short lecture. So dv equals dx dy dz, and this is equal to rho square sine phi d rho d theta d phi, right? So this is my dv. This whole thing is my dv. Don't forget the rho square. And instead of x, you write rho sine phi cos theta. Instead of y, you write rho sine phi sine theta. Instead of z, you write rho cos phi. And a rectangular region in spherical coordinates is of course given by a being between two functions of rho being between two constant values, theta being between two constant values, and phi being between two constant values, such as the blue region in figure 8. Right, so what is let's look at a particular example, right? We want to evaluate this integral x squared plus y squared plus z squared to the power of 3 by 2, where b is the unit ball, right? Now, by unit ball I mean bounded by the sphere, bounded by the sphere, x square plus y square plus z square equals 1. Right? Now, obviously, using using the fact that converting this to type 3 region and using the fact that z lies between using the fact that z is going to lie between 1 minus x square minus y square root over and plus 1 minus x square minus y square. This is going to be very unwieldy and very problematic. So let's try looking at let's try converting this to spherical coordinates, right? So in spherical coordinates, this becomes a very easy looking region, right? So rho goes from 0 to 1, theta goes from 0 to twice pi, and phi goes from 0 to pi, right? Inside the unit sphere. And of course, x square plus y square plus z square is equal to rho square. So the integrand becomes e to the rho cubed, right? Integrand becomes e to the rho cubed, and of course the region is rectangular. So and of course don't forget the factor of rho square here. So this we can express as a product of iterated integrals, product of iterated integrals, right? So this is going to give me 2, we'll go with twice phi, and of course this is whatever you get when you evaluate rho square e to the rho cube, when you integrate rho square e to the rho cube, right? So, but in rectangular coordinates, the integration would have been very difficult. This would have been the integration in rectangular coordinates, Cartesian coordinates, Cartesian coordinates. Now, when should you change the cylindrical coordinates, or when should you change the polar coordinates, right? You consider the symmetry of the situation, right? And see if changing to cylindrical and polar coordinates makes the problem easier. That's when you convert. In the next chapter, what we'll do is we'll look at a way to convert to any coordinate system, right? Any general coordinate system using a change of variable formula called the Jacobian formula, right? And here we will, and this is going to generalize for us sections 15.8 and 15.7, right? Remember in 15.7 we changed to cylindrical coordinates, and 15.8 we changed to spherical coordinates. So we want a formula that will help us to change to any coordinate system, and for that we will be using something called a Jacobian determinant, and that is going to be your last lecture. It's going to be a very short lecture, hopefully, right? Thank you very much for your time.